In today's lecture, we covered two big topics. So one is high order linear differential equation. So if we have a homogeneous differential equation with constant coefficients, then to solve it, we set up the corresponding characteristic equation. It is an algebraic equation, and the roots of the algebraic equation, they give us solutions of the differential equation. So it's pretty much similar to the second order case. Then every real root gives us a corresponding solution, which is an exponential function. Then if it has multiplicity k, then we're going to multiply it by t squared, and so on, until we get the right number. So, and then overall we are going to get k linearly independent solutions. And very similar with complex roots, only complex roots appear in pairs of complex conjugates, and then each pair of complex conjugate roots gives us two solutions of the differential equation, so which are a combination of exponential function and trigonometric functions. And then if we have complex roots of multiplicity k, then instead of just one pair, they give us k pairs of solutions. To construct them, we just take the first and then multiply by t squared, and so on up to t to the k minus 1. Well, the second big topic that we covered today was the Laplace transform. So given a function of a variable t defined on the interval from 0 to infinity, its Laplace transform is another function of another variable s given as a certain integral that we can compute for every value of s, and then it becomes a function of s. So then the Laplace transform may not be defined for all values of s between 0 and infinity. So sometimes it is only defined when s is bigger than a certain number. But in any case, the application of the Laplace transform that we saw today is that we can use this property of the Laplace transform is that it transforms differentiation to multiplication, and then we can use it to solve a second order or even a higher order ordinary differential equation. Well, not just an ordinary differential equation, but an initial value problem, right? So we just apply the Laplace transform to the both sides, and then it gives us an algebraic equation on the Laplace transform of the solution, and then we can find the Laplace transform of the solution, and then by applying the inverse Laplace transform, we can find the solution, and the inverse Laplace transform is applied by looking up the pattern that we got in the table of known Laplace transforms.